This is an advanced higher chemistry video looking at Unit 1, and it is a continuation of our video on atomic orbitals, where we're now going to look at quantum numbers to describe how electrons are found within different orbitals. So remember, each energy or our orbitals are our subdivisions or our subshells of what we have called energy levels or electron shells in National 5 and higher. And each energy level can contain several types of orbital. Each orbital can contain a maximum of 2 electrons, and each electron possesses a fixed quanta or value of energy, which is why you get a discrete line in the atomic absorption or emission spectrum. And quantum numbers can be used to describe each electron within an atom. So you've got to remember that quantum numbers are used to describe electrons. A lot of the information in quantum numbers describes orbitals, but overall, please remember that quantum numbers are describing electrons. So this is our guide to quantum numbers. I will have a slide on each type of quantum number after. So this is just going to be our introduction. So the first quantum number we've got is our principal quantum number. And the symbol we use for the principal quantum number is n. And it can have values of n, and n are just whole numbers starting at 1. The principal quantum number usually correlates to a period on the periodic table. So if an atom is found on period 1, all of the electrons will have a principal quantum number value of 1. And this indicates the main energy level or the size of the orbital. The bigger the principal quantum number, the bigger the size of the orbital. When you've got atoms that contain different principal quantum numbers, depending on the size, electrons will be found in multiple, will have multiple principal quantum numbers. The second type of quantum number is known as the angular momentum quantum number, and this is the one that's going to tell you the shape of the orbital. So it's going to allow you to know whether an electron is found in an s, a p, a d, an f orbital, for example. Now the symbol for angular momentum is L, so that's not a 1, that is a small case letter L. Now the values that L can have, it might seem strange, but they can go from 0 to n minus 1. What this means is that for each principal quantum number, you can get a range of angular momentums. That is because some principal quantum numbers will have s, p, and d orbitals in them. Some principal quantum numbers might only have an s. For example, if you have a principal quantum number of 2, the angular momentum can start at 0 and it can go up in 1s until you reach n minus 1. Now if n was 2, n minus 1 is 1. So the values of the angular momentum could be 0 or 1. But each electron is only going to have one value of angular momentum, and that number tells you the shape of the subshell. So if the angular momentum ends up being 0, that means it's in an s orbital. If the angular momentum is 1, that means it is a p orbital. If it is 2, it is a d orbital, and in a very rare case, if you find out that it's a 3, it will be in an f orbital. You need to remember the symbol for angular momentum, and you need to remember that 0 is an s orbital, 1 is a p orbital, 2 is a d orbital. The next number is the magnetic quantum number. And the magnetic quantum number is used to tell you the orientation of the particular orbital. So remember, we had 3 different types of p orbital, we had 5 different types of d orbital. The magnetic quantum number is used to distinguish between which one of those 3 orbitals the electron is in, or which one of the d orbitals the electron is in. You do not need to be able to understand or use the magnetic number and relate it to an exact orientation. You just need to know how to use the magnetic number, how to go from an angular momentum quantum number to a magnetic quantum number. So the symbol for the magnetic quantum number is a letter M with a small letter L, which helps you remember that the magnetic quantum number is related to the angular momentum quantum number. Now the values you can get for a magnetic quantum number go from whatever your angular momentum was as a negative number through 0 to positive L. What this ends up doing is when you've got your angular momentum being P, you end up with 3 values for the magnetic quantum number because there are 3 types of p orbital. When your angular momentum is 2 for a d orbital, this system of minus L to plus L results in 5 different magnetic quantum numbers for each of the 5 different d orbitals. Finally, you've got the spin magnetic quantum number, which is an M with an S, sometimes just an S, and this tells you the spin of an electron. Now there are only 2 possible values for spin. They can be positive half or negative a half. And you can imagine these as being spinning clockwise or spinning anti-clockwise. The reason why electrons need to spin is because, remember, electrons repel one another. So in order for them to constantly repel one another, they need to actually spin. And if they spin in opposite directions, they're able to overcome that repulsion within an orbital. The reason there are only 2 values for a spin magnetic number is because there are only ever 2 electrons within an orbital. One will have a positive half, other will have negative a half. And the only way you'll need to use this is if you're given the spin magnetic quantum number of 1 electron in an orbital, you'd need to be able to just say that the other electron will have the opposite spin number. Now going into these in more detail, the principal quantum number can have any value from 1 up. It tells you the size. And the outermost electron in any atom usually has a principal quantum number equaling the number of period that the atom is in. For example, hydrogen will have a quantum number of 1. Sodium will have, the outermost electron on sodium will have a quantum number of 3 because it's in the 3rd period. And each principal quantum number can contain subshells depending on its size, giving rise to differently shaped orbitals, which is why you need the angular momentum quantum number to tell you these different subshells. So for every value of n, you can have several different angular momentum quantum numbers. And it tells you the type of orbital. So angular momentum numbers start at 0 and can go up to n-1, remembering that n was the principal quantum number. So if you had a principal quantum number of 1, the angular momentum can only equal 0 because n-1 is 0. However, if you had a principal quantum number of 3, your angular momentum can go 0, 1, or 2 because 2 is 3 minus 1. That's as high as you can go. And you need to be able to relate the value of the angular momentum quantum number to a particular shape of orbital. L of 0 is an s orbital, 1 is a p orbital, 2 is a d orbital. Now the magnetic quantum numbers, these tell you the specific orientation of a p or a d orbital. So remember, each type of orbital can exist in a few different forms. I said 3 there, but that is just p orbitals. So there's only 1 type of s orbital, there's 3 types of p orbital, and there's 5 types of d orbital. The magnetic quantum number allows you to know which specific orientation an orbital electron is in. So the magnetic quantum number goes from negative L to positive L. So in a d orbital, where your angular momentum is 2, your magnetic quantum number can be -2, -1, 0, +1, +2. That's 5 different magnetic quantum numbers. Each one of those corresponds to the 5 different types of d orbital. You do not need to correlate a specific magnetic quantum number to a specific orientation. You just need to be able to relate the values of the magnetic quantum number to the values of the angular momentum quantum number. And so one for each of the 5 d orbitals. If you had a p orbital, the angular momentum would be 1, and the magnetic values would be -1, 0, and 1, indicating the 3 types of p orbital. Now, the final thing to remember is that quantum numbers describe electrons, not orbitals. And every electron has 4 quantum numbers. The first 3 describe the size, the shape, and the orientation of the orbital that an electron is in. So the principal quantum number n tells you the size of the orbital. The bigger the n value is, the bigger the orbital. The shape, the angular momentum, is it an s, is it a p, is it a d orbital? If angular momentum is 0, it's an s orbital. If it's 1, it's a p orbital. If it's 2, it's a d orbital. Then orientation, that's our magnetic quantum number. And we've got to remember that there are going to be, for an s orbital, we're only going to have one possible orientation because it's a sphere. For the p orbitals, we're going to have 3 different orientations, 3 different possible magnetic quantum numbers. And for d orbitals, we're going to have 5 different numbers because there's 5 types of d orbital. The final quantum number, the spin quantum number, indicates the spin of the electron. And if 2 electrons are in the same orbital, their first 3 quantum numbers are identical, but their last quantum number, which is always a half, will have opposite signs. So for example, here we have got principal quantum number of 2. Then we have got our magnetic quantum number of 1, indicating it's a p orbital. Then -1, so they're both in the same type of p orbital, but one electron has a spin of +0.5, one has one of a -0.5. And this is a very common 1-mark question. They give you the quantum numbers for one electron, and they ask you for the quantum numbers of an electron that's paired with that one. The only thing you need to change is the sign of the magnetic spin, that last number. So I know that's been quite a long video. That's because quantum numbers are a more difficult topic to understand. They will come up every single year. So far, there has not been an open-ended question on quantum numbers, but it could easily be something that you could be asked 3 marks worth of material. So please do have a go over this. Do practice past paper questions on quantum numbers because they are significant and they come up every year.